Hello, and welcome back to the Apache Flink learning series. In today's talk, we'll be giving a high-level overview about Apache Flink, and then we'll dive deep into how data flows through an Apache Flink application. Let's get started. We can begin with a definition. Apache Flink is a framework for stateful computations over unbounded and bounded data streams. Starting with the word stateful, we know that from previous sections of this learning series, this means we're talking about application state. In other words, we're retaining information about data after it's been processed or seen by the application. Apache Flink can perform stateful computations. Next, we have unbounded and bounded data streams. Unbounded data streams would be ones that have no fixed start and end. They're continuous, in other words. This is in contrast with bounded data streams, which are analogous to batch jobs with a fixed start and end. Apache Flink can do both. Some other notable key features of Apache Flink would be exactly once state consistency guarantees, and those are achieved through the statefulness within the application. Data stored durably in state is not processed twice. Apache Flink can also handle late data with its event time and watermarking capabilities. Apache Flink has a layered API set, including Flink SQL, table, data stream, and process function APIs. These decrease in abstraction and increase in the amount of state control you have as you increase, respectively. Apache Flink is highly available and fault tolerant due to its checkpointing mechanism and the ability to run an Apache Flink cluster to withstand outages, lost nodes, and corrupt data. And Apache Flink is highly scalable, capable of processing millions of records per second at low latency. Depending on the connecting systems used and the type of data processing you're doing, this type of scale is definitely possible. Apache Flink could be used in many different use cases, including but not limited to event-driven applications. These would be keeping track of stateful computations along the way. Streaming or batch data analysis. Apache Flink can process streaming and batch data with minimal changes to the code. ETL jobs. You can transform and load data into a variety of different data systems using Apache Flink. Anomaly detection. With Apache Flink, you can leverage built-in anomaly detection capabilities to identify anomalous data. And with the expressiveness in Apache Flink's APIs, there really are few use cases Apache Flink can't accomplish. It's important to remember that Apache Flink is not just an analytical framework. It's an application framework that can be used for analytical and operational use cases. Now that we've learned a little bit about Apache Flink, let's take a look at how data flows through an Apache Flink application end to end. So suppose we have a data set of all the taxi trips that were taken in New York City. The Apache Flink application will cover, in this use case, will receive a stream of taxi trips and count the number of trips per destination, these being the major airports, over a specific time period. It will then send those updates of these counts to a destination as they occur. On this screen, we see the anatomy of an Apache Flink application. Every Apache Flink application will look something like this, containing a source on the left-hand side, which receives data from an external system. We also have a series of different transformations. Transformations can be a simple one message at a time transformation, like this map on the left, to extract the destination. Or they can do some sort of aggregation, like counting the number of trips per destination. And then finally, we'll have a sync where we will send the data outside of Apache Flink when we're done processing it. The programming model where an application is defined as a sequence of processing steps is called the data flow model. Now, data flow is not unique to Apache Flink, but it allows you to represent almost any application where data flows through. Let's see how this works in a little bit more detail. When you write your application, you actually code something like this. You would code it to count trips per destination. And in order to do that, we need to split, partition, or key by the data before we count. We know that Apache Flink scales horizontally. The application Apache Flink deploys, based on the data flow you defined in code, will look something like this. Let's pretend we want two parallel processing flows. The source is parallelized. If we're reading from a proportioned input, like an Apache Kafka topic, source partitions are then distributed. We would then extract the destination, sending the trip to the next operator, and that operator would then count the number of trips to that destination. Periodically, the count would be sent to the destination. It's important to note that data is partitioned based on the destination here. All trips that go to the same airport are arriving on the same count operator instance. Additionally, application state, the counts per airport, are partitioned the same way as the records that are flowing through the application. So why are we doing this? The running count is one of those stateful operations that we've learned about in previous videos in this learning series. The running count of trips to each destination is contained in the state of our application. Flink is a distributed system which can run on multiple machines. We can partition the data so that all trips to the same destination arrive on the same machine, guaranteeing that the count of a specific destination is on a single machine. The application state can actually be stored on the machine itself. The benefit to doing this is so that we don't have to make remote calls to a data store in order to update the count. This would additionally give us lower latency when we want to do things like update the state, and allows us to scale horizontally, adding more machines as we partition the state further. It's important to remember it's not just processing that we're distributing in Apache Flink. It's also the state. In order to understand the future videos in this series, as well as some Apache Flink documentation as you're reading through, let's define some common Apache Flink terms, just so we're all on the same page. The flow of operators you define with your application code is called the logical graph. Each of the steps in your logical graph is called an operator. Sources and sinks are also called operators, but they're sometimes referred to as the source operator or the sink operator. When we deploy our application, we decide what level of parallelism we want. Application parallelism is how our job is parallelized into instances of operators. And this becomes the default parallelism for all operators in the graph. Taking into account the parallelism and the flow between operators, Apache Flink generates a physical graph. This is what actually gets deployed onto the Apache Flink cluster. Based on the parallelism provided, multiple instances of each operator are deployed. These parallel operators are called subtasks. Each operator generates a number of subtasks equal to the parallelism. To recap, the application flow based on our code defines the logical graph. A logical graph is a DAG, or a directed acyclic graph. The logical graph is composed of operators, one or more sources, some transformations, and one or more sinks. When we deploy our application, we choose the parallelism. Based on this, and the data flows between operators, Apache Flink generates a physical graph composed of subtasks. And that's it for the definitions. Stay tuned for the next videos where we dive deeper into Apache Flink and Apache Flink concepts. As always, thanks for watching. Leave your questions in the comments, and we'll see you in the next video.